Welcome to our presentation of EDICT. This is Bram presenting. Our motivation here is that if you're in a slope field and you take a step according to that slope field at every time interval, you do this for some amount of time, and then you try and reverse this process, stepping backwards along the slope field. You don't start where you end up, or you don't end where you start. And this is analogous to DDIM inversion in deep diffusion models. So what we propose is a method that actually is able to invert itself perfectly, invertible diffusion process. And we apply this to editing as shown on the bottom left. The core idea is that we create an exactly invertible diffusion process. We invert images to noise latents with some caption, and then we modify the caption and denoise to edit. So that process is shown here. You take a photo of a statue, you noise it, and in our method, we can get that back perfectly if we ask for a statue. Okay, now I can slow down that the minute is done. So EDICT is invertible, so you're always going to get that statue back if you use the same caption, and then that also means that if we generate with a different caption, a statue with raised arms, we actually find that a lot of the other details are preserved along the way. We're going to dive into some math, so here I'll show some more pretty editing results of taking a cupcake on the top left and converting it to different captions for a lot of different fun desserts. The key idea is that we're actually going to track two variables to perfectly invert the diffusion process to make sure that we're never losing information. A typical diffusion step will have some form a lot like this. Xt minus 1 is equal to some coefficient times xt plus some coefficient times a noise prediction on xt. This is DDIM. That second term, though, it's not invertible due to that nonlinearity. We propose a set of invertible equations. So here at each denoising step, starting from xt, you actually are going to track two variables, xt and yt. This is inspired by coupling layers and normalizing flows. Doing this, you're actually going to take the noise prediction at the other point. These xt and yt start equal, but you're going to take the noise prediction at the other point and use that to move yourself. So xt is going to move based off yt is going to move based off xt. And this is a coupled invertible version of the diffusion step. And then we're also going to add in a contraction layer for stability, which is an invertible averaging layer. The reason we chose these equations like we did is that all of these can actually be reversed. All of these are linear solves. So you can solve for y of t and x of t given xt minus 1, yt minus 1, or here we're incrementing from t to t plus 1. So you're going to reverse that dilation layer, or reverse that contraction layer, which becomes a dilation layer, and you're going to reverse that stepping layer. We test this generative process out on the right, so we're setting xt equal to yt at the start. That'd be the same as our xt in the diffusion process, and you're going to generate forward. If we don't have this mixing layer or the contraction layer, we see that this doesn't work as well. But if you have this contraction layer there, EDICT looks pretty much identical to the baseline. So by adding in a second step at each diffusion time step, a second unit call, we're able to actually replicate this process while keeping everything invertible while shown on the left. You can give an image, say x0, set y0 equal to x0, and reverse all of the way to latents. We test this out. So we take an image and we put it to its noisy, or deterministically noise it with some caption and then come back. And we see that EDICT is able to pretty much exactly, any variance is up to the VAE because we use stable diffusion here, is able to reconstruct the image. But if we try and do this with DDIM sampling naively, like DDIM unconditionally, even without a caption, or especially if we try and do this conditionally with guidance scale, I believe, equal to 3 here, we destroy information in the image and don't get the same thing back up. We have COCO reconstruction errors on the right, which we discuss in the paper. EDICT maintains excellent detail preservation during the editing because of the fact that it's invertible, because when you're going back and forth, the only changes are going to be stemming from that caption. There's nothing systemic. So we have EDICT on the right column for a few different captions. And if you pause the video, you can note some different details that we're doing a really good job preserving here. We also look at quantitative metrics. So we look at clip score on the bottom right, or clip score on the bottom and LPIPs on the y-axis. So the bottom The x-axis is how well did you incorporate the edit, and the y-axis is how faithful were you to the original image. We flip that y-axis because we make it consistent, so up and to the right means better. And we test out different baseline DDIM methods, including using DDIM in conjunction with prompt-to-prompt alongside EDICT, shown in the gray circles. We show that we establish a new frontier with EDICT. The different numbers are different levels of inversion strength, but for any level of clip score, so any level of faithfulness to the new edit, EDICT offers the best way to maintain faithfulness to the original image. Our final thoughts here are that the invertible processes can open up a lot. Here we just showed a preview that we focused on in our paper of editing, but there are also other things that invertible processes can do. They're very cool and exciting. Again, normalizing flows are a great literature source to kind of look at how powerful invertible processes or neural networks are. Latent distributions are still very understudied. We can invert the diffusion process, but we actually find that when we invert this diffusion process, we don't end up really on the manifold. You don't really end up on the Gaussian VAE manifold, or sorry, not manifold, but distribution. You don't wind up in that Gaussian distribution. When you reverse, you actually can wind up quite far outside it. So that's something interesting that's pretty understudied. There's a lot of real images that actually the point that maps those real images is really far away from what normal diffusion random draw at xt would be. And there's also improvements still to be done algorithmically here. So while we focused on EDICT, or while we focused on kind of those 4 sets of equations, there's a lot of benefits you could imagine, such as if you look back at this contraction layer, it's necessary for that stability, as I showed, but it also makes things actually difficult in this reversal because it's a dilation layer that can exponentially expand. So yeah, there's still improvement to be done algorithmically. We're happy to talk about more about this at the paper, at our poster rather, about the paper. It's some of the math can get a bit crunchy, which is why I kind of glossed over it for the purpose of this short presentation. But we really appreciate you watching. We'll be at poster Thursday, PM 184. And again, if you want one takeaway from this paper, it's that Euler doesn't return home in a slope field, and that's what DDIM is doing. If you go forward, you're not going to find your way backward, and we managed to do this properly by tracking 2 different quantities. Now I have 8 seconds left. Look on the right to see what I mean qualitatively. Thanks.